Okay, so today in this video we continue with chapter 4. Chapter 4 is about magnetism. So in this chapter you have some subtopics. You have 7 subtopics. And for this video hopefully we can cover subtopic 1 and 2, which is about magnetic field and resultant magnetic field by current carrying conductor. For subtopic 4.1, which is about magnetic field, you need to be able to draw the magnetic field lines, and you need to understand what is actually magnetic field. Okay, magnetic field is actually, by definition, is actually region where magnetic force is experienced. So any region around the source of magnetic field that experience a force is where we consider as magnetic field region. So here I show you two types of magnetic field. One is a uniform magnetic field, and another one is non-uniform magnetic field. So the magnitude of magnetic field can be represented by the distance ataupun numbers of magnetic field lines per unit area. So I can say that if I have 7 magnetic field lines, the magnitude of the magnetic field is actually higher compared to, let's say in this example, 4 magnetic field lines. Okay, so for uniform, basically you have a parallel line like that, and compared to non-uniform, you can see that the lines is actually diverging. So on the same cross-sectional area, like this one and that one, for the first part it only covers 1, 2, 3, 4, 5 magnetic field lines, but at the end here it's only covered 3. So the difference there shows that it is actually a non-uniform field. Okay, so remember, if you have a parallel lines, indicates it is a uniform field. So all magnetic field across here are the same. If you have a non-uniform, you can see that the lines are not parallel. Okay, the direction of magnetic field lines, this is a symbol that we use. For into the page, the symbol that we use is cross like this. Okay, sometimes without the circle, just a cross like that. For out of the page, it's a dot line like that. It's circle, and sometimes the circles are not drawn. And then this one, the same for current and other direction as well. So I just put this one as magnetic field, but in fact this one valid for all directions or quantity. Okay, this one is some of the examples for magnetic field lines that you guys need to be able to draw. Let's say if they ask in the assignment to draw, you should be able to draw lah. So this one is for bar magnet. If you have one, I think this one, you learn this one in school, there shouldn't be a problem. The key thing here is that the magnetic field line is going out from the north pole, going in the south. Okay. And then the same case applied for horseshoes ataupun U magnets. You can see that from north it's going out, okay, and then from south it's going in. And this is the shape of the magnetic field line. So if you have more than one bar magnet, like in this example, this one is actually full bar magnet, right? The north is over there, the south is over there. So if you have unlike poles like this one, north and south, you can see that it shows attractive field line. Okay, compared with the light poles, where the field line actually repulsive. This point here is what we call a neutral point, where magnetic field is equals to 0. Okay, again, you need to be able to draw. So you just have to refer to your lecture notes. Okay, so there are a few examples like this one: long straight wire, circular coil, solenoid, and earth magnetic field. So your task is that I want you guys to try to draw the remaining one. Okay, draw it yourself. You can find it in the internet or you can find in your lecture notes, and try to draw it yourself. Okay, so what is magnetic flux density? So it is represented by the symbols B. We use symbol B. Sometimes you can see that it has a arrow over there that indicates that this is actually a vector, so it's a vector quantity. By definition, it says that magnetic flux per unit area across an area at the right angles to the magnetic field. So that means this one is magnetic flux per area. I think later on you learn about magnetic flux where phi is equals to BA. Okay, but for now, we just want to focus on the magnetic field itself. So the unit for magnetic field that we use is Tesla. Okay, the phi here is magnetic flux, which is represented by a unit Weber, and area is meter squared. So in a way, you can write this one as Weber per unit meter square. Okay, that's it for 4.1. Again, you just need to be able to draw the magnetic field line for different examples, and then you need to understand what is actually magnetic field line itself. For 4.2, you have to calculate a little bit. You need to be able to calculate 3 examples of magnetic field source. So the 3 examples are long straight wire, circular coil, and solenoid. And for that one, you have 4 particular equations. Okay. For a long straight wire, this is the first example. Not the first example, first cases for a long straight wire. The formula to determine the magnitude would be B equals to mu naught I over 2 pi R. Okay, but at the same time, because magnetic field is a vector, you still have to determine the direction. Okay, to determine the direction, you can use what we call right hand rule. And to apply the right hand rule, your thumb is actually directed towards the current direction, and the remaining fingers is actually your magnetic field direction. So you can see that your fingers actually curl, right, curling towards circle. So this is the example. I mean, if you really want to see this one, maybe you can do it yourself, and you can take an object like a pen or something. Okay, you imagine that the pen is pointing in the same direction of the current, like this one going up. So if you put a paper over here, you can see that the fingers actually curling in that direction. Okay, so if I want to draw in 2 dimensions, so this is basically the top view. Basically, I see this one from the top like that, and is it from the top? So you can see that the current is going out of the page. So I just write it down. And if you want to do the right hand rule, you can put your thumb going out of the page. Then you can see that your fingers are curling in anti-clockwise direction. And if you have current that is actually going into the page, so you will have this one as X lah instead, right? So your thumb is pointing towards the page, into the page, and your magnetic field will be in that direction. So that one will be clockwise direction if the current is into the page. So you really need to understand the direction of current and magnetic field using your fingers. To calculate the magnitudes are simple. B is equals to mu naught I over 2 pi R. This one valid only for long straight wire. Mu naught here is equals to 4 pi times 10 negative 7. That one is permeability constant of a free space. I is the magnitude of the current. 2 pi is 2 pi constant. R here is the distance from the wire. Okay. For example, if I have a wire in that direction and they ask you to calculate at point P, that means this would be my arc distance. Okay. Again, magnetic field is a vector quantity and the units is Tesla. Our next example is circular coil. Next case, case number 2 is circular coil. Again, if you want to determine the direction of magnetic field, you have to use right hand rule. So in this case, maybe you can try to take a circle object. Normally I would use something like my cellophane tape, and then just put my thumb in this direction, right? So I will have my fingers that are in that direction. I'm not sure whether you can see that. So your thumb is in this direction. You have to use the right hand and don't use the left hand. So your fingers is something like that, which is curling towards that direction. Okay, so in this case, your magnetic field will be pointing in that direction. If you can't see this, you can PM me directly later. To calculate the magnetic field, it's quite simple. You have to use the formula B equals to mu naught I over 2R. Okay, and remember this magnitude of magnetic field is at the center over here. Okay, and again R is the radius of the loop. If you have more than one loop, so let's say you have multiple circular coil, that it was being put together like that, kan? So you have to multiply by numbers of loop, multiply by numbers of n. Okay, and then the last case will be solenoid. Okay, to determine the direction of magnetic field for solenoid, again you have to use the right hand rule. But this time, instead of putting current on my thumb, I can put my current on my fingers so that my magnetic field is my thumb. That means in these cases, you can see that all the currents are going downwards. Is that right? For the front part. So this solenoid actually, from this one, let's goes in front. This one is the behind part. Okay. So this is the front part, the front part, the front part. So you can see that the front part here is going downwards. So if I want to draw my fingers, say this is my hand and this is my thumb, right? So what I mean is that my direction of current is downward, so I use that one for my fingers. This is my current direction, I, and this would be my magnetic field direction. So in this case, my magnetic fields are to the right. Okay, and if you have the opposite direction of current, then you have an opposite direction of magnetic field. And to calculate the magnitude, you can use the formula of B equals to mu naught Ni, but remember this one is small n, that is equals to capital N over L. Capital N means numbers of turns. How many turns are there? If you have 100 turns, then this capital N becomes 100. And then length is the total length of the solenoid. This is the length. And if you substitute this one inside there, you get this value. Sorry, this formula. Okay, this one at the center here. Point X, which is at the center. If it is at the end, at the end of the solenoid. So you have to multiply by half. So the value is actually half compared to the center. Okay, now for the fun part, let's try to look at some of the example on how to calculate the magnitude and the direction, how to determine the direction of magnetic field. Okay, first example, it says that determine the magnetic field strength at point X and point Y from a long straight wire carrying current of 5 amp as shown below. Okay, so direction of the current in this case is to the left, this one, and they ask you to calculate the magnitude of magnetic field over here and over there. Okay, let's try to calculate that one. So at point X, okay, and then if you get this kind of example in exam, the first thing is that you have to determine which formula you want to use. Okay, this is a current carrying, sorry, it's a straight wire carrying current. That means this one is a long straight wire. So you can use the formula of B equals to mu naught I over 2 pi R. So current is given 5 amp, mu naught is 4 pi times 10 to the 7, and the R is the distance. So for point X, R is equals to 2 centimeter. Obviously you have to change to meter. So R for at point X is equals to 2 times 10 negative 2 meter. Okay. On the other hand, at point Y, R is equals to 6 times 10 negative 2 meter. So if you want to use that formula, B equals to 4 pi times 10 negative 7. This one corresponds to mu naught. Current is equals to 5. So you have 2 pi and then 2 times 10 negative 2 or 0.02. So you can cancel out the pi, then this becomes 2. So you can press 2 exponent negative 7, oops, 2 exponent negative 7 times 5 divided by 0.02. I got here is 5 times 10 negative 5 Tesla. Okay, and then using the same formula, you can calculate at point Y. B equals to 4 pi times 10 negative 7. So you use the same current, so 5. The distance now becomes 6 times 10 negative 2. Okay, again cancel out the pi and 2. I got here is 1.67 times 10 negative 5 Tesla. Okay, that one is for the magnitude. How about the direction? Even though the question doesn't ask you to state, maybe you can state as well, because this is a vector quantity. So if you want to determine the direction, I can put my thumb in the direction of current. So this would be, my fingers will look something like this, right? Okay, nampak cacat, but it's okay. I think I understand. Okay, so this is my current direction, which is to the left, and all my fingers, if let's say I put a pepper over here, right, it will be pointing into the page. So over here, direction of magnetic field is into the page. On the other hand, it will be going out from this part, right? So that one is going out. So I can say that at point X, my magnetic field is going into the page, and at point Y, it's going out of the page. Okay, so basically at point Y, if I want to redraw, okay, my thumb is like that, and then my fingers are like that. It's pointing out of the page. Doesn't look like a hand at all, so I'm gonna erase that part. Oops, come back. Okay, anyway, so that's how you determine the magnitude and the direction of magnetic field. Okay, moving on to the next example. This one, example number 2. Says that a closely wound circular coil of diameter 10 cm has a 500 turns that carries a current of 2.5 ampere. Determine the magnitude of magnetic field at the center of the coil. Okay, this one it says specifically that this is a circular coil. Okay, and it has a 500 turns and diameter of 10 cm, carries a current of 2.5 ampere. So if it is a circular coil, you can use the equation of B mu naught I over 2R. Okay, for circular coil, they will ask you to determine the magnitude at the center only. Tak ada yang dekat end. Kalau yang solenoid baru ada dekat end and at the centers. At the center. So in this case, they give you several information. I just took out the information. They give you diameter, so maybe I can change to radius, which is half of the diameter. So it becomes 10 over 2 times 10 negative 2. I change to meter as well. This one becomes 5 times 10 negative 2 meter. Turns is n. Okay, but you can see that from the formula that I use, there's no n because that one is for single circular coil. Okay, so for number n loops, so therefore this one becomes b n, oops, just multiply by n. Okay, so n turns is equals to 500, I is equals to 2.5. Then you can substitute all the values inside the formula. So B equals to 4 pi times 10 negative 7. Numbers of turns are 500. Current is 2.5. And the radius is 5 times 10 negative 2. You press the calculator. You try to press it yourself, because sometimes students don't know how to calculate 4 pi times negative 7 too. Okay, I forgot to put the 2 here. So it's arm, the formula got 2. So I got here is 1.57 times 10 negative 2. And the unit here will be Tesla. Okay, so here it doesn't say or it doesn't give you any direction, so you don't have to determine the direction. If they did give, then you have to determine. The question B says a solenoid. Okay, so once it says a solenoid, you know straight away you have to use formula for solenoid. It gives you the length 2.6 centimeter in diameter, current of 18 amp. Magnetic field inside the solenoid is 2.3 millitesla. So inside means the center lah. Calculate the length of the wire forming the solenoid. You want to find the length of the wire. Interesting question. Okay, so maybe I can try to redraw the solenoid first. Okay, roughly it's like this. So it does not represent the actual numbers of turn. I just draw it like that. So it says here the length is 1.5 meter. So that one is 1.5 meter. And then 2.6 centimeter in diameter. So that means my radius R half of the diameter. How much is that? 2.6 divided by 2, you got 1.3 times 10 negative 2 meter. And then current of 18 ampere. Again, they didn't give you direction, I just put it in that direction, I. Then it says that the magnetic field inside the solenoid, maybe over here, B is equals to 2.3 millitesla. Okay, and then the question want to find the length of the wire forming the solenoid. Okay, okay, you can see that this one is actually the given value L here is actually the length of the solenoid, not the length of the wire itself. So what you're gonna need to do actually, you have a formula of solenoid. B is equals to mu naught n L, sorry, mu naught n I, where small n there represent n over L I. Small n represent n over L, so substitute that, it becomes that formula. And since it is at the center, it doesn't have the half. Okay, if at the end, you have to multiply by half. So this is the formula that you're going to use. What you guys need to do is that you can find the numbers of turn first, and after you have the numbers of turn, okay, you can roughly calculate the circumference size, and then you can multiply with numbers of turn so that you can get total length. Okay, you calculate numbers of turn first. B here is equal to 2.3. For pi times 10 negative 7, you can find n. I is equals to A, is it 18? Yes, 18. I just double check. And L is the length of the solenoid, which is 1.5 meter. So I can rearrange everything and solve this one. I got here is 152.52. Okay, so that means I have 152.5 to circle. Okay, so each of the circle required how much wire? So to calculate that one, I can calculate circumference S, which is equals to 2 pi r. Okay, so r is given so it requires 0.817 meter for one turn. Okay, because the question actually want you to find the length of the wire, right? So the length of the wire required for one turn is 0.817, and you have 152.52 turns. So the total length okay, so this one I got, what should this? 124 before. Okay, I think I have pressed the calculator wrongly. It should be 0.0817 over there. So no wonder my answer seems to be off. Okay, now 0.0817 multiplied 152.52. I got hit 12.46 meter. So this is the total required wire to produce this solenoid. Okay. And then we're moving on to the last example, and the last example is actually from your tutorial questions. Okay, it says that determine the magnitude and the direction of magnetic field at point Q due to the current I equals to 1 ampere flowing in a semicircle with a radius of R equals to 2 centimeter, as shown in figure 4.2. So they want to determine at point Q over here. Okay, so by logic, okay, magnetic field here are being contributed by three segments: segment AB, segment BC, and segment CD. But for segment AB and CD, it only produces magnetic field on the left and right hand side around it, but not in front or behind here. So this segment contributes to zero magnetic field over here. The only segments that contribute will be this BC, and this BC is actually half of a circle, semicircle. So to solve this one, I can apply circular coil equation. So you know that circular coil, the formula for magnetic field is B equals to mu naught I over 2R, right? But if you want to use semicircle, it will be half of that. So magnetic field B here is equals to half mu naught I over 2R. And then to solve this one, you just substitute all the values. I is given, so half 4 pi times 10 negative 7. I is 1. R is 0.02. I change to meter. Okay, so I got here is B equals to 1.57 times 10 negative 5 Tesla. Okay, and then you have to determine the direction of magnetic field, because this one is a vector. So put your thumb over here. How to draw? Okay, maybe I can draw it like that. So you can see that actually your fingers is like that. Right. So this is the direction of current. So roughly in that direction. So this one is actually going out of the page, magnetic field. Okay. So the direction is out of the page. As a conclusion for this subtopic, you have three main cases, which is straight wire, circular coil, and solenoid. Okay, but you have four formula. So straight wire will be B is equals to mu naught I over 2 pi R. Circular coil B is equals to mu naught I over 2R, and solenoid would be two formula, B is equals to mu naught N L ataupun mu naught N L, sorry, that one is not L and this one is I, mu naught I, change this one, over L. This one for center. At the end of the solenoid, you have to multiply by half. Okay, and then to determine the direction of magnetic field, you have to use right hand rule. So you can represent your thumb with the current, or you can represent your thumb with the magnetic field. It depends on the situation. Okay, the other fingers would be the other one lah. Instead of current, maybe you have the magnetic field. Okay.